Hello. So this talk was originally presented at the Lockpicking Village at DEF CON in 2025. And I had intended to have it recorded and streamed it onto the internet for people who couldn't make it to come and see. And I had a few people, especially on the LPU Discord, asked me to make sure that they could see it after the fact. And I don't think it ever actually got recorded. So I thought we would have a go at recording it live now that I'm at home. I did have some audio issues at the conference. I wasn't able to play a couple of the videos that are in this slide deck. So yeah, but we're going to have a go at recording it. I'm going to run through it. It should take probably about 45 minutes, and hopefully we'll be able to get that out onto YouTube. So this is magnets. How do they work? We're going to talk about picking and decoding magnetic locks. And yes, there will be a lot of magnet memes in this talk. So real quick, my name is James. I am at 206 on most platforms. Those of you on Discord know me as 2. I am on the target ops team at Trusted Tech, so my day job is red team stuff. This is not a red team related talk, but TS do fly me out to conferences and give me research time, and let me put these things out there for everyone to enjoy. So shout out to them for being awesome as always. I've been picking locks probably for around 15 years, taking it what I would call seriously for kind of the last 5. Like something happened around 5 years ago that made me stay indoors and work on hobbies inside. I can't think what it was, but yeah, kind of been that important, right? I am, for those of you who know the LPU belt ranking scale or the Reddit lockpicking subreddit, a black belt 10th Dan picker. For those of you who don't know what that means, essentially it means I've picked an awful lot of very, very hard locks. And I am also a registered locksmith in the UK for various reasons, not really related to this talk. So what are we going to talk about? Well, for our purposes, we're going to talk about any lock that has a key in it that looks like this on the bottom here, right? So a key with magnets in. We're not going to talk about these things at the top. These are known as maglocks. They are electromagnetic device used in access control systems. We're not interested in those, but if a lock has some sort of magnet in it and a traditional kind of key looking thing, that's what we're going to cover. So before we get into it, we're going to take a brief look at the history of magnets in locks. Now these are all from Google patent search. It's actually quite hard to find patent images from other countries outside of Google. So obviously this is my research based on Google patent search, so bear that in mind. So we start off, the earliest reference I could find, 1937, with this Mr. Ratcliffe filing a patent for a magnetic locking key. It's the first one I could find where a magnet was actually intentionally used as a security element in the lock. Obviously this has long since expired, and I couldn't find out anything else about this lock, right? So I couldn't find any examples of it being made, any information on Mr. Ratcliffe, where he worked or anything like that. So if anyone knows about this lock, I'd actually be really interested in learning more. Fast forward a little bit, 1947, we see Hal Cooley file this patent for a magnetic actuated switch. This is interesting. It uses a magnetic keycard, which we'll see some examples of those later on. Again, long since expired, and I couldn't find any evidence that this was ever made, similar to the previous lock. If you know about this lock, I would be really interested in learning more. Essentially, this works by putting a magnetic keycard in there, and that causes the circuit that's connected to this to energize. Current flows when the keycard's inserted, and the thing can work. So moving on to 1964, we see Schlage, as in that Schlage, file a patent for a magnetic keycard-based lock. And this actually goes on to be released as the Schlage core key, and we'll see an example of that later on. So sticking in the 60s, late 60s this time, we see this patent filed, which goes on to become the Miwa EC, at least according to LockWiki anyway. This is interesting. The patent wasn't filed by Miwa. It was filed by, I think, Fujitsu, another kind of company in Japan. For those of you who don't know who Miwa are, they're a Japanese lock manufacturer. They make a lot of locks. They're still going. They've made an awful lot of locks with magnets in them, and we're going to see a lot of their stuff as we go through this talk. So in 1980, we see Miwa file 2 more patents, and these go on to become the Miwa 3800. So the EC has 3 variants I'm aware of. They keep adding top pins to the lock, so a ball bearing detent, and then we see 4 pins and then 6 pins. At the end of the 70s, beginning of the 80s, that kind of changes to be the Miwa 3800, and that supersedes the EC range. This was also released under the Anker brand name as well, so you might see these sold as the Anker 3800. It's the exact same lock, just sold under license. Then again, 1983, we see the Miwa VM78 appear in a Miwa catalogue. Now, I couldn't find out when this was actually released, but it was first in a catalogue. This catalogue is dated 1983, first reference we could find on it. And these are the locks that are used in the Sega arcade cabinet. So anyone who's into retro gaming, these Sega locks were used in some of those cabinets, and we see Sega branded keys and things like that. And we've got some examples of those as we go through the rest of this talk. And yeah, huge thanks to Devo on the LPU Discord for the screenshot of this catalogue. Similar sort of time, 1984, we see this patent, which relates to the EVA MCS. Now, this was actually developed in 79, released early 80s. I'm not sure why this patent is in 84. No idea why that happened. This one is interesting. Its patent's been refreshed a couple of times. It's still available. You know, we can still go and buy the EVA MCS today. You can go to the EVA website and you can buy this lock. You can buy a complete system of MCS, and it's actually a fairly high security lock. A bit more recently, then 1997, we see Sysum patent this pin tumbler tubular kind of design hybrid thing. Sysum are a French lock manufacturer. Again, they are still going. They're still producing magnetic locks, things like the Sysum Atlas. They do some security fastenings, like bolts that need a magnetic tool to unscrew, things like that. If you know French locks, they have this like pump lock design. This is big pump lock vibes, right? I'm not going to get into the history of French locks or anything like that in this talk, but you'll see a lot of similarities between their kind of designs and other mechanically based pin tumbler style French locks. And then more recently again, 2002, we see this Matura patent for a key with a single magnetic element in it. This is a dimple lock. There are standard pin tumbler elements in this lock as well. They're just not in this diagram. This is interesting. We start to see this move from magnets being used for the main security element into stuff like this, where we really have one, and its purpose is more like key protection, anti-bump, those kind of things. It doesn't contribute a huge amount to the overall security of the lock versus like the elements in the other locks that we've seen so far. And then obviously there are a whole lot more, right? We're just scratching the surface here. We see things like the Miwa VM99, which is still available. This is a fairly recent screenshot from a Miwa catalog where it's there next to the LS7 and those kind of locks, which is LS7 is a high security cam lock used in casino systems. There are a whole load of other examples from Japan, and obviously lots of patents I didn't mention. This is a long and complicated story about how these evolved. If you're interested in that, Lockpicking Forensics does have a great article on it where they go through the timeline of these kind of things, and they actually list which lock the patents go on to be part of, right? And I used some of their research in the previous slides. So let's take a look at the different types of magnetic lock. So for our purposes, broadly speaking, there are two types. We have ones where a magnet is the primary locking mechanism, so it contributes the most to the overall security of that lock. So that would be things like the EVA MCS, the Miwa MagCam, Sysum Atlas, those kind of locks. And then we have ones where a magnet is a secondary element, so the Avarice ABS, the Avarice Magtech, Matura C39. It's basically one magnet on the key that kind of adds a little bit to the overall security of the lock, but it's mostly there for other purposes. Now, there is technically a middle category here of what you could call a hybrid kind of lock, where things like the Miwa EC, the 3800, the VM99, they have magnets and they also have pin tumbler stacks in them as well, right? And we can't really tell what is the primary locking mechanism in there. It could be either of them. For our purposes, we're just going to lump them all into the primary mechanism category because it's fairly easy. But just be aware that there is a middle category there if you want to get really pedantic about it. So some examples. On the top row, we have a Dissec magnetic disc brake padlock. This one is interesting. It doesn't have a keyway. It just has this faceplate where the key goes. We have a maglock, not to be confused with the electromagnetic kind. This is a key and knob style out of a US door mechanism. And again, it has this faceplate with a key that looks like a little circle rather than a traditional key. We see the EVA MCS, the LZM, Capital Industries MagCam. At the front, we have the VM99 and the Miwa magnetic cam lock. This is actually one of the Sega branded ones, and we're going to take a closer look at that later on in the talk. Some more examples. This is a Schlage core key at the back. We have the later version of the Miwa EC, the one with the 6 top pins. A Caden lock at the back. That's essentially the same mechanism as the Schlage core key. I think they're actually made under license. And you can see the cards for those in the middle row there. The lock in the middle row underneath its card is another Caden style lock. It's the same mechanism. This is actually a cover for another lock. So we see these a lot in Japan. They fix over an existing lock and provide an extra layer of security. There's a whole history of lockpicking in Japan and why these things exist, which is outside of the scope of this talk. But if you're interested, you can find me on socials and I'll talk to you about it. The bottom row, we have this little magnetic padlock with this kind of interesting key. It tensions off this weird kind of circle shape in the middle. And then the bottom right, we have another one of those key cover things. This is designed to fit with a Japanese style door lock. And then some of the more interesting types. These are some that use magnetic key cards. So a Miwa and a Shower example. These are credit card size keys. And this one at the back middle is off a magnetic safe. And it has this kind of key that's just a bar full of magnets. And we're going to take a little closer look at that later on as well. Some examples of what we call secondary mechanism then. We're not going to spend too much time on these in this talk at all. They're not that interesting. But a rebrand of the Avis ABS at the front there, the Matura C39 and the Avis MagTech. The MagTech is interesting in that it is a traditional pin tumbler style lock, right? Most of these are dimple locks that we see because it's easier to fit the magnet in. The Avocet, the MagTech, the key actually has a magnet on the bottom of the key, which you can see in the screenshot there. So let's look at the different types of locking mechanism. Now, again, broadly speaking, there are 3 types, and yes, getting AI to draw these diagrams is incredibly frustrating. This was the best I could do. So we have these 3 types of locking mechanism that we find in these locks. Broadly speaking, we can categorize them as things that slide, things that rotate, and things that look like pins. This will become more easy to understand when we see some pictures, right? So things that slide, these are magnetic sliders. This is that Sega little magnetic cam lock, the Miwa one. So if we look at this bottom left picture, we can see it has 3 sliders. One is in the clamp, it's actually upside down, so you can see the magnets on the bottom. And they are spring biased so that they push out from the core and they interface with something in the lock body to stop the core from turning. In the top picture, you can see when the key's inserted, they're fully retracted into the core, so that's there, like the lock is open position. And then in the exploded view at the bottom, we have the 3 sliders, they're springs, this little key retention thing on the top left. And then these 2 ladder-looking things are what the sliders interface with in the lock body. So that's where the sliders stick, those little protrusions, and that's what stops the core from turning. Now, the 2 magnets on the bottom of these sliders are there for a reason, which we'll get to later. But it is a purposeful design choice that they have these 2 magnets on the bottom of these sliders, which, again, we've got slides on that later on. Things that spin, so this is the LZM taken apart as far as you can non-destructively. And this has these little metal discs inside it. We call these rotors. So these are little metal discs. In this example, half of them is lower than the other half. So a semicircle has been kind of cut a little bit lower. They have 2 magnets on the back, which north and south, and they align using the key such that those low spots are all in a row in this slot. And the slot is called a sidebar slot. So when the key is inserted, you can see all those low points are in a line, and that creates enough space in there for a sidebar, which is that brass piece in the right-hand photo, to drop into that slot when you apply a little bit of tension. So this is a sidebar-based lock. It has 2 sidebars, one on either side, so 6 rotors in total. And when you take the key out, you can see in the right-hand picture, those rotors bias such that the high points, which you can see in that photo, actually fill that sidebar slot. So sidebar can then no longer depress into that spot and the lock won't open. Similar kind of design. This is the MCS. And if you look at the right-hand photo, this is the rotor out of one of these. So this one has 8 rotors in 2 sets of 4. It's a similar idea. The low point in this is not a cut. It's this little wedge that's missing from the perimeter. And that's the true gate. There is no concept of false gates in these locks, only true. If you want to do mastering on these locks, you just add more cuts in this rotor, right? But they work in a similar way. They spin around. They have 2 magnets that align to a specific angle. That's the bitting. And then the way this lock actually works is a sidebar will slide backwards and forwards, which is kind of out of the scope of what we're trying to cover here. But if you look at the left-hand photo with the key inserted, you can see that all those notches, the gates, are aligned such that those slots in the rotor cover are open, so something could slide forwards and backwards in there. When the key is removed in the middle photo, you can see that those notches are now biased such that the grey part of this rotor is filling that slot. So now nothing can slide in there, and that's what keeps this lock from being opened. And then finally, we have things that look like pins. So this is a version of the Avocet ABS taken apart. In the first photo, you can see there's no pins or other stuff in it. I've taken all those out. But we do have this element on the last pin chamber, which is just this kind of free floating magnetic element. And it's not spring loaded or anything like that. It just sits in the core and it sits below the shear line. Above it is a traditional spring and pin tumbler style pin. And you can see the pin in the middle photo. So when this is in its key removed locked state, the spring pushes that pin into that hole and then the shear line is blocked and the core can't turn. When the key is inserted, so the middle photo, the magnet in the key actually lifts that magnetic element up to the shear line, which in turn lifts the pin, and then when everything else is set, the shear line is open and the lock is able to turn. Right? The only thing remarkable at that is there's no physical connection between the key and that element. We have to manipulate it with a magnet rather than a traditional lockpick. And then this photo on the right is the Decoding flip down cover that we saw earlier, just taken apart. And this thing works with just a load of these little magnetic pins in. These are all magnets, and they all have an orientation to them. So north or south is facing one particular way. And when the key card's inserted, they all kind of move to the correct position. And this metallic fence that you can see in the photo above them, that will then slide and the lock can open. As a side note, if you ever take one of these apart, be very, very careful because there are about 12 maybe magnets in there, and if you drop it, you'll have a magnetic jigsaw, which will be a lot of fun for you to put back together. So how do we tell what mechanism we have? Well, the obvious one, which isn't on the slide, is you can just go and ask people, right? So go on like the tool forums, the LPU Discord, those kind of things, and ask people who've seen this lock before. There's very little chance that you'll see a lock in this category that nobody's encountered before. It's quite uncommon to discover a new one of these. Let's say you did. You've got a few options to figure out what's in there, right, without taking it apart. You can look at the key. You can look at the keyway, the lock body, and make some educated guesses. You could use Google and try and find like manufacturers' information about it, exploited diagrams, CAD renders, that kind of thing. LPUbelts.com, they have a lot of like exploded view, we call them gut pictures of locks. Maybe somebody has taken that one apart and submitted a photo, you didn't know about it yet. Or a previous version. If there's a model, like a later model of an older lock, you might find that there's a lot of similarities from like a gut picture of a previous model. Patent searches, if you can find the patent, that will get you all the information you need. And magnetic viewing film will help you with some of these tasks, like looking at the key. So what does that look like in practice? Well, let's take the top key here on the left. This is the LZM key. Looking at it, we can see it has 3 round magnets. There's 3 on either side, so 6 in total. There's nothing else going on that key. There's one little cut there that's likely for key retention, but there's no pin cuts or key control or anything like that going on. And then if we look at the middle photo, this is the LZ lock body. You can again look down the Bible and see that there's that one ball bearing down there. There's nothing else going on in there, so it's unlikely to be a mechanism that lives in the Bible. It's ruling out like pin-based systems like we'd see in like the Avocet ABS. Looking at the core, there's a lot of space around there, right? So you could fit maybe sliders in there. You could definitely fit sidebars in there. And we can rule out sliders pretty easily by looking at the amount of material that's actually available in that lock body. Like there's a lot of material in the core, but not much in the lock body itself. So there wouldn't be much for a slider to actually grab onto and interface with. So it's kind of leaning us towards it being a rotor-based sidebar system. And then if we look at the key under the magnetic viewing film, this pattern is the stereotypical rotor-based pattern. We have these circles, they're split, so they're a north and south pole, and they're all at different angles. So we can safely say that that is a rotor-based lock. Then looking at this Matura key, it's a dimple lock, first of all. So there's a lot going on. We have some key control bits. We have your normal pin tumbler cuts that you'd find in a dimple lock, and we have a single magnet. It's round, okay, could still be a rotor. It's unlikely to be a slider based on its position and its geometry. And if we look at the lock body, yes, this is the wrong photo. It's the ABS lock body. They're very, very similar, and for all intents and purposes identical. There's just a little bit more going on in the Matura lock body. It doesn't matter. But if we look at it, we can see there's a lot of pins and things in the Bible. We know that there's key control and stuff as well. That's going to be on the other side. So there's quite a lot going on in there. There isn't a lot of space to add sliders and rotors. Similar thing to the LZ, there's just not much material in the lock body for sliders to interface with. And then if we look at the key under the mag viewing film, it's a solid dot, so that will rule out rotors. So it's a fairly safe bet that this is a pin-based system, which is indeed what it is. And then I've put a close-up of this Sega key in here because at first glance, this could look like a rotor-based system. Like we have these two blobs per magnet. And it's not. It is definitely sliders, which we can tell from looking at the lock body and things like that. The reason these are here is to do with key space issues, which we'll cover later on. But you can also rule out rotors by looking at the orientation. They're all in the same line and they're all in pairs. So yeah, just a bit of a red herring that I thought was interesting to kind of throw in there. But practically speaking, this doesn't matter, right? So the type of locking element is irrelevant when we approach picking them. We approach it in the same way regardless of what's in there. So it could be a pin, it could be a slider, it could be a rotor. We're going to attempt to pick them in the same way. The only time it matters is when we want to figure out if we're dealing with a lock with a single element, the ABS, the C39, etc., because we largely approach those in a different way. We try and bypass those, right? We will just move that magnetic pin out of the way, either by sticking a magnet down the keyway or lifting the pin with a magnet on a stick, something like that. We don't tend to get the same feedback. And once it's done, it's done. We don't have to revisit it. We just pick it like a traditional pin tumbler lock at that point. So figuring out if you're dealing with one of those is really the only time you need to worry about it. So how do we pick them? Well, we need some tools, right? We still need a way to manipulate the magnetic element, and we need a way to tension the lock. The theory is exactly the same as picking any other lock. We're going to use the jiggle test to discern the states of the elements in that lock, but we still need a pick and a tensioner, just like you would in a traditional pin tumbler lock. So we need magnets, right? We can't use traditional picks. If we're interfacing with a magnet, we need another magnet. Neodymium are the best bet for this. They're the right trade-off of size, strength, and cost. The best choice is likely to be a 2 mil by 1 mil disc magnet, so a round magnet. They also come in 0.5 mil thick. Those are also pretty good for things like the MCS and those locks with narrower keyways. But you can get away from most locks with a 2D1 mil disc, so that's what I'd suggest you buy if you want to start exploring picking magnetic locks. A known pole magnet, like you'd get in a kid's science kit, could be useful. It's not essential. I've never used one for picking. Knowing that the polarity of the magnet you have on your tool is different is all you really need, unless you want to get into things like decoding, which you'll see later on. And then we need a way to get the magnet into the keyway, right, and back out again, hopefully. Old picks work great for this. So if it's a keyway-based, traditional-looking key lock, then a magnet glued to an old pick or something like that is ideal. If it's one of those ones that we saw earlier, like the mag lock or the dissect disc brake lock, which just has a face, an ejector pin, a hex wrench, something like that, that you can stick a magnet to the end and wiggle it kind of like a pencil, that's really what you want to look for there. So here's some of my tools. These are a couple of old picks and a decoding tool with a magnet glued to the end. The glue is there just to give it that little bit of bias towards not flying off and sticking to something inside the lock, right? So we can easily get it out again. An ejector pin, you'll note there's no magnet glue to this. I just stick them on and wiggle it. And when I need to change the polarity, I just turn the magnet over. This 3D printed plastic red piece at the bottom was designed for one of those card-based systems. It's a non-ferrous tool with a magnet stuck in the end, and there's a matching opposite pole one of those somewhere in my spare parts box. And then this orange broom-looking thing on the right was a rotor manipulation tool. So it has two rotors, two magnets even glued in there. They are opposing polarities, and I was using that to just precisely align a rotor on, I think, that dissect padlock. I don't use that much, but it's just there as an illustration that you can actually make custom tools for some of these locks as well. And some other tools, these are a couple of examples of magnetic viewing film. So the one on the left is the cheap version. It doesn't self-reset, so we get these streaks in it, but it is very flexible and it's very cheap. The one on the right is the high quality one. It's very expensive, actually ludicrously expensive for what it is. It's self-resetting. It gives you a bit of a clearer image, but it's encased in this plastic. You don't really want to cut it. It's not flexible. So having access to both is actually quite useful. If you were going to get one, I'd suggest a cheaper one, at least to start with. And then some magnetic shielding. This is a thin alloy that just diverts the magnetic field away from other stuff. And that helps with picking locks like the MCS, where they're incredibly well made. and actually letting off tension to manipulate one rotor can cause you to accidentally unset another one just by having the magnet near it. So that can be useful in some locks, but very, very uncommon to actually need that. So we've talked about picks, now it's time to talk about tension. We have to tension the lock. Things still bind just like they do in regular locks. We still need to figure out what state each element is in. It's not always as easy as you'd think, so there are lots of weird keyways in these locks. Once you remove the need for a key-shaped thing to manipulate pieces of metal inside a lock, you can actually get some very interesting key designs. And the only way I've really found to tension these properly is to just spend lots of time in CAD, right? So CAD and then 3D printing, that kind of workflow is really a winning strategy for these kind of locks. Sometimes we just can't tension them at all, so there is no way of tensioning them. That does effectively make some of these locks, quote, pick-proof. You can still bypass them in most situations. We'll see some examples of that, but suffice to say at this point, there are magnetic locks that are pick-proof in the traditional sense. So here's some examples. This is that Capital Industries magnetic cam lock. It actually tensions off that shaped part in the middle. The key is that shape, and the only way to tension this really is to print something, which is what I've done here. This is a CAD drawing and then 3D printed tension control device. You can't tension this lock with a traditional turning tool. It's just there's no material there for you to grab onto and turn. This dissect padlock, the only way you can tension this is by actually pulling on the bolt. The spring in there is quite stiff. This particular example is well used and abused. It doesn't tension very nicely. I tried to tension this enough to single pin pick it, and it's just impossible, at least in this example. You can't get a good grip on that bolt. Your hand will cramp. You can't attach a tool to it easily. It's effectively pick-proof. You can bypass it, which is how I got it open. We'll talk about bypasses later, but it is almost impossible to tension this off the bolt. And then this magnetic safe lock, this is the kind of safe that this thing would be in. And again, thanks to Devo for grabbing me this picture. This actually has a little switch on the back. And when you put the key there, that switch can kind of depress and work. When the key's not there, it doesn't. It just depresses a little bit. So in this out of the safe state, first of all, we'd have to be manipulating something that would be inside the lock. So you couldn't really tension it that way. You could argue that maybe you could just make an exception and try it. There isn't enough feedback there to really isolate individual elements. It's a very small travel switch, and you'd have to kind of jam your finger in some metalwork at the back to get to it. Picking it in the safe, apart from like violating the core principles of lock sport of not picking locks in use, right? Let's say you took a door off one of these things and like made it lock sport appropriate, for example. You're still talking about a handle linkage through some other stuff to this tiny switch, and I don't believe there's enough feedback there to allow you to single pin pick this lock. But you can definitely decode it, which we'll see in a few slides' time. So we need to determine the pin state. We're going to use the jiggle test, and there's only 3 states in these locks. It's actually a little bit easier than a traditional lock. There's no underset or overset in these. And the states we need to figure out are binding, set, or not binding. Now we have no physical contact with the locking element, so we can't use spring feedback. We can't use the wobble test like we do in a disc detainer lock. We can't, like rely on levers clacking against fences and stuff like that, like we would in a lever lock. So what do we use? Well, it turns out we can use sound. Right? Sound is really the only feedback we have, and it works perfectly for these locks. So when an element is binding, it will produce no sound. It can't move because it's stuck, so that there's no sound there. When you hear this free movement sound, which I'm going to try and play a couple of videos in a minute, I'll hopefully explain this, but for a rotor, for example, you'll hear it just kind of spinning around without any interference. For a slider, it will be clacking back and forth, similar kind of sound of a pin. This means it's not binding yet. When you get a weird clicking noise, this is very obvious with rotors and a little bit more muted with sliders and pins, but still discernible. If your rotor goes from a spinning sound to a click, 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 that is telling you that it's set. And you can use a combination of this feedback to figure it out as well. So if it's binding under tension, you release tension, manipulate the element, apply tension again, and you still get a moving sound, it's likely to be set, right? And then sliders and pins, the feedback does differ. It's just slightly harder to figure out the difference, but it's absolutely possible when you start getting into this, you can totally figure out what that sound is. And yes, don't worry, I have examples. So I'm going to run this video. I'm going to hope that it picks up on the recording setup, but this is me demonstrating the sound on one of these Sega cam locks. It's not the best recording. We're going to let it play, and then I have another recording of me actually picking this lock where hopefully the audio is a little bit better. So let's let this one play. Hello DEFCON. We're going to use the Miwa MagCam to understand the audible feedback when we're manipulating locking elements in magnetic locks. So to start with no tension applied, I'm going to manipulate the back slider and we shall hear it free moving in there. So we can hear that slider just kind of clacking around in there. Next, with tension applied, I'm going to do the same thing and we'll hear no sound because it will now be binding. There we go. Now I'm going to attempt to set that slider. And that slider is now set. So I have some tension applied and it is clacking around in there, and the sound is ever so slightly different to the free floating sound. And if I repeated that process for the other two sliders, the lock would be open. So this is a good time to call out this tool that I don't have in the slides, but this red thing attached to my vise is a acoustic pickup that you can use on a guitar or something like that. And it goes off to a little guitar amplifier, and then I would normally put it on headphones for this demo. I was running it into a recording setup. But this tool can actually be quite useful, especially if you're old like me and struggle with your hearing. This can absolutely help you discern those sounds a little bit more clearly. So, hello. There we go. We're going to go to the next video. This is me actually picking this lock to open. It's going to take about 3 minutes, but I'm going to talk through my approach to picking this lock. And this will translate to pretty much any of these locks. The core principles are the same. This one's just slightly easier to pick. So let's let this one run as well. Hello DEFCON. We're going to pick the Miwa magnetic cam lock. So it does work. It is fully pinned. We're going to pick each part all the way open, and I'm going to tell you my approach to these as we go through it. So the first thing we need to do is find our binding element. This one is not binding. So now we're going to try the front one on the right. Not binding. The one on the back is binding. So we're going to set that just by releasing tension. We're going to manipulate the slider. And that is now binding. So we'll test this front pin again. Still not binding, so it has to be the left hand slider. So we're going to swap our tension over so we can get into the other side of the keyway. And now the important part we need to consider is tension control. We want to release just enough tension to set the slider. But not so much that we drop the other pin. There we go, so that one is now set, and you can see we've got this core movement as well. In this lock, that indicates that we are getting closer to the open. So we should still have this back slider set. We can check. Yep, still set. So now we have to be on this front one, and we're going to do the same thing. There we go, the lock is open. Okay, so raking with extra steps, right? It's precision single pin raking. This applies to all mechanism types, as we've already said. Rotors can benefit from a specially designed pick where you have a set of picks with the known like rotations of the elements on them. Rain on the LPU Discord actually made one of these for the MCS, which can help with picking it. It's not essential. I've never used them, but just know that they do exist, or you could make your own. So the TLDR is take a magnet on a stick, wiggle, 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 do your tension control, and that's how you approach picking these locks. If you were going to get into this, I would suggest starting with something like the Miwa Magcam. The one that I have only has 3 elements. They do come with 4, but they're a very approachable lock. It's only 3 elements. You can progressively pin them. They're a great way to kind of learn the tension control and feedback that you need before you get into harder locks. But you can certainly progress through the LPU belt system almost entirely on magnetic locks, which is fairly interesting. So that covers picking as much as is feasible in a 45-minute talk slot, right? Any other examples I could show you would just be a similar kind of wiggling a magnet in a stick with slightly more steps. So I'm going to show you some other attacks that are possible against these kind of locks as well. Now, you would potentially think that math is the main weakness of these locks, right? So magnets can only be a north or a south pole. Hopefully that's not a huge revelation to anyone. And this can drastically reduce the key space. We'll see in a couple of slides' time examples of that. And it allows us some decoding attacks as well. And in some locks, it could allow us to create tryout keys, depending on how the lock has been manufactured. So those of you who are into crypto and those kind of things might have been looking at that the Miwa Magcam, thinking it has 3 sliders, 2 polarities. So does that mean there's only 8 possible keys? Well, no. In a different lock, if it was designed by somebody else, maybe. Remember I showed you it has 2 magnets and the key has lots of magnets. The Magcam actually has some defenses against this. So those magnets on the slider actually can be different polarities. Magnets in the key can be different combinations of polarities, and they work kind of in unison. So one will start to pull the slider into the core, and then another will take over and repel the magnet, and those kind of combinations. It actually makes it a little bit more complicated, bumps it up to a few thousand possible keys. The Miwa EC has 14 possible pin locations in the key, but as few as 6 can be populated. All the examples I've got, I've only got 6 in there. So that would only be 64 possible combinations, which is well in the realms of tryout keys, right? The only problem is we need to know the locations of those magnets first. Now, when these locks were designed, kind of the early 80s, rapid prototyping like we have today didn't exist, right? We couldn't 3D print keys on the fly, in a couple of hours. You'd have to actually have either a metal casted key or buy actual blanks and things like that. So there was some kind of assumed defenses against this kind of thing. But these days, it's well within the realms of possibility to figure out the locations of those pins in the lock. You can do that with a magnet on a stick or a Hall effect sensor or other things that we'll cover in a few slides' time. And once you know the locations that are populated, you could very quickly assemble 64 possible tryout keys. Now, later versions of the EC had pin stacks at the top and things like that, so you'd also have to consider, do you want to make a bump key or those kind of things? But if we ignore that and just focus on the ones that have like the ball bearing key retention detemp, it becomes the realm of possibility, right? I'm not suggesting that this would be a valid attack against that lock, but it does illustrate the point that you can potentially get into these weird math-related issues if you're not careful when you're designing these kind of locks. And you may well find some from less reputable manufacturers that are vulnerable to this kind of thing. So I actually tried to create a tryout key set for this Miwa Magcam. I wondered whether modern, science and technology and more powerful magnets would allow us to overcome this kind of 2 magnet on a slider, multiple magnets on the key style of defense against this. The intent of this was to produce a set of 8 tryout keys for this lock, right, which I thought would be an interesting addition to this talk. And I got pretty close, so it's fairly easy to model this key in CAD. It doesn't take more than half an hour. And then just glue some little neodymium magnets into it, right? And I got pretty close. So look at the middle picture, you can kind of see I've got it. So these sliders have all retracted into the core. This core will then go in and out of the lock and will turn. The only problem is it needs a little tap to push the sliders to a point where the magnets will take over and snap them in place. And I just couldn't overcome that when the lock was installed, like actually fully assembled in the lock body. I tried. There's a whole bunch of prototypes that I tried there that all failed. I still think there's mileage in this research. I think if you put a little bit more time into changing the location of the magnets, the angle of which they're set into the plastic and things like that, I think it might be possible to actually create a set of triac keys that would work in this lock. For me, I'm kind of finished with that research. Like I can pick these locks in under a minute. It's kind of irrelevant. It was an interesting detour while I was putting these slides together. If you're interested in carrying that on, I will give you all the CAD files and things like that I have, all my notes. Let me know, and I will quite happily send that to you. And if you feel like carrying that on, but for me, I don't think the juice is worth the squeeze. But it was an interesting kind of learning experience anyway. So decoding, we've mentioned this a couple of times already, so let's explore how that works. Some formats of these locks can be very easily decoded, i.e. that pick-proof lock from earlier. All magnetic locks, with a few exceptions, things like the rotor-based locks, they can all be decoded. The rotor-based ones are just a little bit harder. You can still do it. You can still learn the individual rotations of those rotors through audible feedback, but building the tooling for it to manipulate, set a rotor inside the lock, take that out, find the next binding one, release tension, figure out that binding element, all the rest of it, just becomes quite an exercise in tool making. So possible, but not particularly fun. Something like this, though, this lock works by having magnets just behind this metal face, right? And if you hold another magnet against that face, you can use the attraction repulsion of same pole, different pole magnets to figure out the polarity of the magnet that's actually in that spot. And then you can design and print a fake key, like a makeup key, which is what I've made here. And you can put the corresponding polarity magnet into the correct spot. So not all magnets are populated in these locks, they're kind of a random position. So you can figure out the position and the polarity that it needs to be and create a key by following this step by step. You don't need access to the key to do this. If you're interested in how that works, I have a video on my channel. It's conveniently obscured by the picture-in-picture. But if you go to the channel where this video is published, it's somewhere close to this video in my feed. Right? So if you want to see me do this live, I have a video on it. It takes a couple of minutes, and you can fully decode and open one of these otherwise pick-proof locks. So we've seen a couple of attacks there that are possible just by access to the lock. Right? We don't need access to the key to do those math-based or decoding-based attacks. But if we have access to the key, that opens up another type of attack, so key duplication. And like any other type of lock, if we have physical access to the key, it is essentially game over. Magnetic locks actually benefit from the fact that you can't take photos of them and decode them. Right? So other locks, even quite high security ones like the Protect 2 and things like that, you can take a photo, decode it, and create a key from it. These locks, you can't do that. You can't discern the bitting of the magnetic elements from a photo. But if you have access to the physical key, you absolutely can. And this is known to have been done historically, right? So I'm going to show you a couple of photos from the Stasi Secret Service Tools book. This is by Oliver Diedrichsen. I'm going to apologize in advance. They are photos of photos printed in a book. There's no electronic copy of this book that I could grab screenshots from. Oliver, if you ever see this talk, I would love an electronic copy just so I can more easily translate it, but I totally get that that's unlikely to happen. So anyway, all credit for the following photos goes to Oliver and the Stasi Secret Service Tools book. If you don't know who the Stasi were, they were the secret police in East Germany during the Cold War. They are kind of well known for surreptitious entry and other spy-related stuff. This book is a fantastic read. If you're interested in locks in any way, I really do suggest you buy it. So here's some of the things that they were getting up to. This is the LZM and the Zeiss-Icon System M, which for all intents and purposes is identical to the MCS. It's basically the same lock. So they're doing science to these things, right? Like they're taking these things apart, they're reverse engineering how they work, they're understanding the bitting possibles the possible bitting rotations of the rotors. Oh, that was difficult to say. And then they're designing tools that allow you to decode these keys. Right, so here's a couple of photos of their research. And then they're using that to produce tools like this. So these are decoding tools for these locks where you can put a key in. Don't ask how they got access to the key. We probably don't want to know. But you can put the key into this device and it will read off the alignment of those rotors. And then they have this chart on there that tells you the bitting cuts as well. I think that's what that little chart's purpose is. So you would take this piece of paper that's on the tool, you would mark those locations, and then you would go and give this to someone else who would create you a key based on what you discern from this tool. And then we have the MCS version, the Zeiss-Icon System M version in the middle. This is interesting. It looks like it's actually using the core of one of these locks to make this tool. So they're actually taking part of the lock and then using it to create a tool to decode the lock. And it works in a similar fashion, right? They have a line on the rotor which will align to whatever orientation, north-south, and then they're reading the bitting off this chart and however else they're doing it, writing that down and going and producing keys. Now, in the 80s, when these locks were new, we didn't have 3D printing or modern rapid prototyping technologies. So they actually created a way to create these keys as well. So they were creating makeup keys like this one in the photo on the right. This is a legit key with some of the key control stuff removed. And then little bits added like little screws and stuff like that. So you can pop new magnets in there, screw it all together and create a working key. This is the kind of effort that went into building those things 30, 40 odd years ago, however long ago the 80s was. Nowadays we would just 3D print one of these blanks, right, and just glue the magnets in. That's, we have access to the kind of technology to do that now. But yeah, an interesting kind of glimpse into practical attacks against these used in the past that's still very relevant today. And then the other major weakness of these kind of locks is science. So there are various ways to detect magnetic fields, like Hall effect sensors, things like that. And again, modern electronics has evolved to a point where we can take a Hall effect sensor that's kind of the size of a grain of rice and put it on a flexible piece of PCB and be able to do interesting stuff with system on chip and those kind of technologies to build small portable decoding rigs. This is not a new concept, and here's a patent diagram from 1980 of somebody who designed a tool to decode. I think this is for the Miwa EC style locks. And you can see from this this diagram, it's incredibly complicated. There's a lot of coils going on in here. There's wires running down this key to a box containing a circuit diagram, which I didn't have space to put the image on, but there is a lot going on in that diagram. And I don't know if this was ever made. It was certainly patented. It's a very interesting tool. More recently, we see this presentation from Walter from Tool in the Netherlands, and he actually made a decoding rig for the Miwa Anchor 3800. And he's using modern technology to do this, right? So Hall effect sensors, those kind of things. I believe he actually had quite a lot of influence from Huxley Pig on this. I don't know for certain, but I've certainly heard that could be the case. So yeah, credit to Hux as well if that's the case. But I very strongly suggest you go watch his talk. Right, it's a fantastic exercise in reverse engineering a key, the lock. He goes from zero access to the key to a fully decoded magnetic part of the key, 3D printed, onto a bump key format and can open the later versions of the Miwa the 3800 with the 6 top pins. Goes on to decode and break master keying systems, things like that, all in this lock. It's a very well put together talk. He actually used it as part of his LPU black belt submission. Again, very strongly suggest you go watch this. It is a fantastic example of the kind of weaknesses that exist in these locks. Yay science! So I tried to make one of these. So I actually intended to replicate some of Walter's research for the talk. Just UPS decided to not ship the parts I needed in time. But I did do a kind of budget version of it. So this is a Hall effect sensor, just on a breadboard and an Arduino with some vibe coded sketch on it. And if you put this known pole magnet next to it, you can read the polarity off the magnet, right? So we can discern that it's north or south. The way these sensors work is they produce a different voltage. It's either positive or negative depending on the polarity of the lock. And that's fairly easy for something like a Arduino Micro or whatever this is to turn that into display output, right? That's like a couple of dozen lines of Python. But what we can see here is one of these Miwa magnetic card locks. You can decode the relevant positions in that card with something like this. So on my long list of research projects, which I'm slowly working through, is to build a decoding system for these card locks. So a device that you could put on the lock and it would just go and decode each individual position, and we can replicate a key card. Yeah, a long way down the road for me to actually being able to produce that, because time is precious and I'm incredibly lazy. But this is kind of how these things are made. So I wanted to put this in just to illustrate the point that this is very approachable. If you're interested in doing these kind of science-based experiments with these kind of locks, it's not actually that expensive or that difficult, especially with access to AI now to help you with the coding, right? This is a very approachable thing that anyone can do. Yeah, and that's it. I think for this recording, I may have run over my allocated time slot by a little bit. At this point, I would have stopped and taken questions from the audience. Obviously, this is pre-recorded. If you have questions on any of this, feel free to drop them in the comments, or if you're on LPU, hopefully you know my tag over there by now. You can find me over there. Or yeah, feel free to grab me on Twitter or any of those kind of things. But yeah, hopefully this has been enjoyable for everyone. There's a little bit of editing for me to do, but yeah, that should hopefully be everything ready to get a recording of this talk out for those who are interested. So yeah, once again, thank you very much for watching.